Chapter 4 Homework, Questions 2, 3, 8, 9. Question 2. Regarding the equal likelihood model, what is it? Equal likelihood model is an experiment which has finite number of possible outcomes, and all the outcomes have opportunity to occur equally likely. How are probabilities computed? To compute probability is desired over all possible outcomes. And if you want to compute a probability of an equal likelihood model, you should find the number of ways that the event can occur and divide it by the total number of possible outcomes. And here's an example. This is the 5 top Oklahoma State officials, and the question says find a probability that we obtain the governor and treasurer. There's 5 in here, 5 officials, and out of 5 you will choose 2. So 5 choose 2 is going to be, it's a combination, and the number is going to be 10. And actually these are the all possible outcomes, the 10 ways you can choose. The number of ways, yeah, there's only 10 ways that you can choose 2 officials from 5. And the probability is going to be, what we're looking for is the governor and the treasurer, and out of this, only this one is the governor and the treasurer. There's only 1 that we're looking for out of 10. That's why we get this ratio. 1/10 is going to be 0.1, or you can say 10%. Or another example, in the back you have 3 blue marbles, 4 white, 5 red. What's the probability to drop the white marble? In total there is 12. The total is 12. And out of 12, in how many ways you can choose white? There's 4 white, so you can choose 4 ways you can choose a white marble. That's why we get the probability by getting a ratio of number of white over the total number. That's going to be 4/12, which is 1/3, or 0.33, or you can say 33%. Question 3. What meaning is given to the probability of an event by the frequentist interpretation of probability? It's the proportion of times which the event occurs in a large number of repetitions of the experiment. So you conduct an experiment where you make a large number of repetitions, and that the proportion of times is going to give you the frequentist interpretation of probability. For example, you have a coin and you toss a coin, and you want to find the probability of getting heads when you toss the coin. The large number of repetition, we should use large number of repetition. In here we use 100 times. We toss the coin 100 times. So there's 2 separate experiments. Both of them have repetition of 100 times, and both of them give you a close number to 0.5, because theoretically getting heads from a coin when you toss a coin is going to be 1/2, which is 0.5. And when you conduct these 2 experiments, you still get a close number to 0.5. That's how we do frequentist interpretation of probability. Question 8. Answer if it's true or false for the statements. The first statement says that for any 2 events, the probability that one or the other of the events occurs equals the sum of the 2 individual probabilities. So which means that if there's event A and B, probability of event A or B equals probability of event A plus probability of event B. So that's what it says in here. Yes, this is true, but only if the events are mutually exclusive events, which means that they don't have anything in common. Yes, if the events that do not have anything in common, that's true. But sometimes we have not mutually exclusive events, which means that the 2 events have common outcomes. So if the events have common outcomes, we cannot use this. Why? Because when you do that, when you add the probability of event A plus probability of event B, you count this common part twice, and it's not going to give you the accurate answer. So we should subtract it, and that's going to be the formula. Because the statement says for any 2 events, we say that this statement is false because it's not true for any two. It's only true for not mutually exclusive events. The second statement, for any event, the probability that it occurs equals 1 minus the probability that it does not occur. That's true. How? Let's say that we have the event E in here. The whole thing is always 1. For the probability, the whole thing is always 1. And if this part is for event E, the other part is going to be not event E. And if the whole thing is 1, to find this part, you just subtract the outer part, the outside part, from 1. That's going to give you the probability of event E. So probability of event E is going to be equal to 1 minus probability of not E. Another example, you have a die, and these are all the possible outcomes for a die. And it's and if you want to find the probability of getting 3 drawing or rolling 3 from the die, normally it's there's 6 outcomes and 3 is only one of them, so the probability should be 1 out of 6, which is this one. But how do we do that? By using this statement. So the whole thing is going to be again 1. The whole probability is going to be 1 for all of them, and which are not 3. These 5 are not 3. And when you find a probability of getting these 5, it's going to be, there's 5 outcomes out of 6. So that's going to be 5 out of 6. This is the part that we do not want. And if the whole thing is 1, you basically subtract this from 1 and you get 1 out of 6. Question 9. Identify one reason why the complementation rule is useful. It's useful when there's a lot of things that you should add. For example, in here it says find the probability that a randomly selected form has 50 crystals or more. So it's asking for, it says 50 or more. So if it says 50 or more, it's basically asking for this part. You should add them up, all these numbers. Well, what we know is the whole thing is always 1. And if the whole thing is always 1, well, adding up these numbers is more work than adding up these two. So when you add these two and subtract from 1, you still get the same thing because the sum is going to be still 1. So that's why it's useful to use the complementation rule. If there is more numbers that you should add, just add the less numbers and subtract from 1. You will still get the same answer.